Let us now learn about the different shift operations available in ARM. The very first shift operation that we'll be learning is LSL, or logical shift left. Okay, so what happens here is, for any given register RM, okay, let's assume, okay, if you perform logical shift left on this particular register content, it doesn't matter what data is present here. Okay, let's assume it as some value x. Okay, entire content is shifted to left side. Okay, and obviously when you shift everything to the left, the 31st bit is actually shifted out and initial location will actually be vacant, right? So that is filled with 0. Let's understand this in more detail using this set of instructions. Okay, let's see what's happening there. So let's consider this particular instruction, move r1 comma hash 0x12. It means in this particular register, let's assume register r1, value 12 is stored. In binary, how will we write 12? It is nothing but 0 1 0 0 1 0 0 0, and all this will be filled with 0. Why? Because 4 bits here, okay, it constitutes one hexadecimal value. Okay, so 2 is written as 0010 and 1 is written as 0001. So how will you fill the other values? It will be 0. So the instruction we have here is move r0 comma r1 comma LSL hash 2. It means shift r1 by 2-bit position towards the left side and store that as a result in r0. So what will happen if I perform LSL hash 1? It means if I shift this by 1 position, what exactly will be the result? To know that, we will try to shift each bit here towards the left side and see what result we will get. Okay, as you know, if you shift this entire content towards the left side, last bit is shifted out and the 0 will come here, 1 here, 0 0 1 here, all this will be 0. This bit is shifted out, and what about this 0th position? It's a vacant position, so since it is LSL, it will be filled with 0. Okay, now what was our initial data in hexadecimal? It was 12. Now what is the new data? Group these 4 bits together. What is the value? 4. Group the next 4 bits together. What is this value? 24. Okay, so what you will notice is, if I shift this entire register content 1 times or by 1 bit position, then what is actually happening is original data is actually multiplied by 2, that is 24. Okay, but what is actually expected here, we want to shift our original content 2 times, means 1 time we have already shifted, so this data should be again shifted by 1 bit position and the result generated is then stored in r0. Okay, let's see what will happen if you're performing LSL hash 2. Okay, so this entire content is now again shifted to left side and this value will be shifted out. Let's see what will be the answer. 0 0 1 0 0 1 and all this will be 0. 31st bit is shifted out and the vacant position here will be filled with the 0. Now what is this? This last 4 bit constitutes 8 and this 4 bit constitutes 4. Okay, so what actually happened now, this is nothing but 12 multiplied by 4. So here logical shift left by 2-bit position is generating a result 48 and this is the answer which will now be loaded into the register content of R0, or new value of register R0 is nothing but 48. I have shown carry bit here. Now this carry is a part of CPSR conditional flag. Fine. So the reason I have included it here is because if in case in this instruction, if I add a suffix yes, something like this, then what will happen is the bit which is shifted out, the 0 will be updated in the carry flag. This is one important updation, that is bit shifted out will get updated in the carry flag if in case you use the suffix yes. Other flags will be updated if in case the result that is generated for R0 is 0, then Z flag will be set as 1. If it's negative, that is if your MSB bit is 1 here, that is the 31st bit is 1 here, then N will be set as 1. If overflow is generated, then V is set as 1. So let's move on to the next shift operation. So now we have logical shift right. Okay, so let's assume we have some initial register RM, okay, with some random data. If we perform logical shift right on this particular register content, then this is what happens. Okay, the entire register content is shifted to right side, that is this side. Okay, and obviously when you shift it to right, a vacant position will be created in the MSB, so that is filled with 0. Okay, and what about the remaining bits? All are shifted to the right side. Okay, so this particular operation is equivalent to, that is LSR hash 1, that is if you shift all the content by one particular bit position, it is equivalent to performing divide by 2. Okay, but one thing we should remember is you will get the exact proper division happening. You can say it if in case you have taken an even number like this. If you take odd number, only the integer obtained while division is retained, while the fractional parts are ignored. That is, for example, if the value here is 3, 3 divided by 2 is actually 1.5, but you will just see 1 in the answer. Let's move on to our actual instruction here, which is move R1 comma hash 0x80. Okay, and we want to perform logical shift right on this particular data 3 times or by 3 bit positions and store the result in R0. So how will you write 80 in binary? So this is 80 and remaining bits will be nothing but 0. Okay, so here if we shift the entire content towards the right side by 1 bit position, okay, then in the first LSR operation or LSR hash 1, what will be the result? Okay, entire content shifted to right means what will happen? This is how it will get shifted, and the 0th bit is actually shifted out. All other contents are shifted towards the right side. Let's see what is the result here. So this value was 80. Now what is this value? This is 0 and this is nothing but 4. Okay, so you can clearly see divide by 2 operation being performed. Now this is nothing but the first logical shift right, or we have shifted this particular data towards right side, okay, by 1 bit position. What will happen in the second round? It is similar to performing LSR hash 2. So what will be the answer you get? It will be nothing but, okay, so this is nothing but 0 and this is nothing but 2, which is again divide by 2. Okay, now what will happen in the third round? That is nothing but LSR hash 3 and our expected output, this is again shifted, okay, towards the right side. Okay, so what will happen? This will come here and all this will be 0. So what is this? This is nothing but 0 and this is nothing but 1, which is 10, which is nothing but divide by 2 operation happening on this particular data. And now because of this particular instruction, this value hexadecimal 10 is the data which will be stored in the register R0. So LSR here is performing divide by 2 for every logical shift right by 1 bit position, because in our instruction we had to perform 3 shift operation. So what we can see is nothing but our result is divide by 8. Okay, that is nothing but original data divide by 8, which is nothing but 10, which will be stored here. Now in this instruction, we have not added yes suffix in order to set the conditional flags, but if in case if it were move s, in that particular case the last bit shifted out would be stored in the carry flag. Okay, and based on if it's this result is 0, whether it is negative, whether it is whether any overflow is generated, based on that other conditional flags of CPSR would be updated. Next we have the concept of arithmetic shift right, which works almost similar to logical shift right, except for one main difference. That is, if you consider this to be some register RM, okay, with same 32 bits, this is supposed to be shifted to right direction, correct? That time a vacant spot will be created in the MSB. What happens in logical shift right is that this particular spot will be filled with 0. But in the case of arithmetic shift right, the vacant spot is filled with sign bit. What is sign bit? Sign bit is nothing but the MSB bit of the original data. If the original data had MSB bit as 0, then all vacant spots created every time a shift, that is arithmetic shift right, is carried out, all those will be filled with zeros. But if the original MSB bit was 1, in that particular case every time a vacant spot is created, it is filled with a value 1. Okay, let's understand this better using this particular example. Okay, so we have our initial value, okay, of R1 as 0x8 and all zeros. How will we write that in binary? This is nothing but 8 and all others are 0. If I perform ASR, that is arithmetic shift right, once on this particular data, what should happen? All the content should be shifted to right. That is the first thing that we know. So all this will move in this direction, right? And the last bit is shifted out. So this is what is expected. If this was logical operation, we know this particular location should be filled with 0. But this is arithmetic shift right. So what we have to see is what exactly is the MSB bit of the original data. Because it is 1, this vacant position is filled with 1. So now what is this? This is nothing but C and all these are 0. So the answer you will get in the first step is C, then C and all zeros. Okay, so that is a result for arithmetic shift right of this data by 1 bit position. What if we perform arithmetic shift right by 2 bit position? What will be the answer? This entire content should be now shifted towards the right side. Okay, and this value will be shifted out, and this content, what will happen when we shift it? You will get answer something like this. And what happens to the vacant position? It is again filled with 1. Okay, so this particular procedure of filling the vacant spots with sign bit preserves the sign of the original data. Okay, now this is the case if in case MSB bit was 1. What if we had some instruction like move R1, hash 0x, all zeros, and last 2 bits are something like this. Here MSB bit is obviously 0. How will it change the output? Let's start with the first case. How will you write this in binary? All this will be 0. How will you write F? and 0 here again. Okay, now if you perform a right shift operation, that is arithmetic right shift, first thing that will happen is all content will be shifted towards the right side. So how will that happen? So we have shifted all the data here. So what happens to the vacant position? It will be filled with 0 because our MSB bit of the original data is nothing but 0. What exactly is this answer? This is nothing but 8 and this is nothing but 7. Okay, what happens in the next state? Again this gets shifted towards the right side. Okay, and the 0th bit is shifted out. So you will get something like this. Now this particular vacant position should be filled with 0. Okay, and what exactly is this answer? This is C, this is 3. 3C is the final answer stored. And now if in this particular equation if I add a yes, what will happen? The bit which is shifted out, that is nothing but the last bit whichever is shifted out gets stored here. Okay, now this is a two stage of our arithmetic shift right by 2-bit position. So the very last bit which is shifted out will be stored in the carry flag, and since the MSB bit is actually 0 here, n will be 0, and because the answer is not 0, z equal to 0, and since overflow is not generated, v is also equal to 0.